please feel free to interrupt if you have questions or anything like that. This is meant to be a very kind of accessible, basic talk about the Reidemeister Trace, which is something that I've been working. I was working on a paper this summer about the Reidemeister Trace. Although what I'm about to tell you, is all going to be like 1930s era mathematics concerning the Reidemeister Trace. So nothing too fancy. Let's do it. So this is going to be about topological fixed point theory. That is, so we care about fixed points of functions. A fixed point, so you have a function from one set to itself, and a fixed point is any point with f of x equal x. And those they come up often in applied problems, although I have no special knowledge of applied fixed point theory, but they are stability points of transformations. There's a lot of people who are interested in fixed points for a lot of different reasons. The basic trick which we use to kind of look at topological fixed point theory is that the fixed points are where the graph of the function intersects with the diagonal. What I mean is, so here's the standard function. I'm going to draw something like this, right? That's a typical function that we would look at, and what I just said, the fixed points are where the graph intersects the diagonal, because this diagonal line is y equals x, and then this is whatever my function is, and the intersection points would be when those two things are equal, which is to say f of x equal x, right? So the fixed point, this is the basic way that we're going to be looking at the fixed points throughout what I'm saying. Oh no! Something crazy is happening. Oh, it's back. Is it back?
Yes, they're more in focus.
Okay. Okay, great. Sorry about that. Where the graph intersects the diagonal. All right. And as you probably know, topology, they say, is like rubber sheet geometry. It's kind of like geometry, but we don't actually care about specific distances or angles. We more are talking about the structure of shapes if you allow them to sort of bend and wiggle around, but not cutting and tearing. That's not allowed, but that's what topology is about. And so yeah, I'm going to consider all of the spaces you should think of as sort of wiggly. Like I just drew a picture which was basically a function from R to R, but it doesn't have to be R. It could be some kind of wiggly line rather than the straight line. And we also want to consider the functions to be wiggly. This is what is different about topological fixed point theory from other types of fixed point theory. I'm also going to consider the functions to be kind of non-specific. Like I just drew a function, but when I draw that function, I don't really mean that particular function, but I mean for that function to be representative of many different functions that you could get by wiggling that one around. So the basic question in topological fixed point theory is, how does the fixed point change when we wiggle the function around? Because I want to consider the function kind of in a topological way rather than in a strict geometric way. The fancy word for this is homotopy. That's what I mean when I say wiggle the function around. The technical word for that is changing the function by a homotopy. So this question, how does the fixed point set change when we change the function by a homotopy, by wiggling around? I'm going to try and wiggle this around a little. Grab that. See that? I'm wiggling it. And as I wiggle it, you will notice the fixed points, that is the intersections with the diagonal line there, they do change while I'm wiggling it, although I would say they don't change in a wild way, right? When I wiggle, those 3 points just kind of wiggle a little bit, all right? So that's what I mean when I say there is some regularity to this. It's not like you wiggle the function and the fixed points change wildly. So there's some hope that we can get somewhere by thinking about the functions topologically. One thing to say is it's easy to add wiggles into the function to create arbitrarily many fixed points. For instance, if I start with a function on the left side, I can wiggle it in the following way. I could add some extra little jiggly wiggles like that, right? That counts as changing the function by a homotopy, because all I just sort of modified the picture in this region by a little bit. But you will agree, this created many fixed points, and in this same way, also, this is no longer a function. Right there, it goes back on itself. I didn't mean to do that. In this way, I said we can add wiggles to create arbitrarily many fixed points. So the general question of how can we change the set of fixed points by changing the function, it's not interesting to ask about can we make more fixed points. The answer is yes, you can always make more fixed points. This is a more interesting question though. Generally the focus is on minimizing the fixed point set by changing the function by wiggling it around. All right, and that is much less clear what can be done. Can you always remove all the fixed points? Actually, you can't. If you think about this example right here, no matter how you sort of wiggle that function around, I think you can't get rid of all the fixed points as long as like this end starts up here and this other end starts down here. So minimizing the fixed point set is the more interesting question. How does the fixed point set change when we change by a homotopy? There's two main ingredients that we focus on, and they are the fixed point index and the Writemeister classes. So I'm going to try to talk about each of those things. Looking for my clock here. First ingredient is the fixed point index. So every isolated fixed point carries with it an integer fixed point index. And in the one-dimensional case, which is all the pictures I've been drawing so far, are one-dimensional in the sense that the domain of the function is R, a one-dimensional line. In this case, the index is always just going to be a sign, +1 or -1, which describes how the graph is crossing the diagonal. So if the graph goes like this, then this counts as a +1 index. And if the graph goes like this, sorry, I should make it a real live function. If it goes like that, then this counts as a -1 index. All right. So the fixed point index is just about it has to do with orientations of everything right where the graph is crossing the diagonal. And then it's also possible to have a 0 index, although that's kind of a special case. That would be when the graph touches the diagonal sort of tangentially like this, but doesn't actually go through it. So this is an index 0. All right, this is the fixed point index, at least in the one-dimensional. You know, in sort of real life papers about this stuff, it's all done in arbitrary dimensions, in which case the index is a little more complicated. But for this talk, we're just going to look at one-dimensional. All right, those are the fixed point index. And I will have you notice these signs, the fixed point index, here's an example with the indexes labeled, they are preserved when I jiggle around the function a little bit. You will see, as I change this, you know, those 3 points will move around a little bit, but they still have those same signs. Like the crossing is still in the same direction if I only move the function by a little bit, right? So the fixed point index is preserved by small homotopies, that is small wigglings of the function. What about, let's say, bigger homotopies? Like in this case, I could actually move this function so that I'm going to change it so that this lumpy bump actually comes down past the diagonal. So then it would look something like this. Maybe make it just barely touching. And you will notice a wonderful fact. When you do this, the index is additive. So what happened here was a -1 and a +1. Those 2 points, sort of during the motion when I moved this thing down, those 2 points gradually got closer and closer together until they actually combined into a single point here. And by sort of the magic of the fixed point index is that it is additive. When a -1 and a +1 combine, they make a 0. When a +1 and a +1 combine, they make a +2. That's actually not possible in one dimension, but it can happen in higher dimensions. So the index is additive. And a 0 fixed point, you probably already realized this, can be removed entirely. Like if I just wiggle this a little bit, it becomes that, which has no fixed point at all. So when you see a 0, that's a signal that this fixed point is kind of not important, or it can be removed by the homotopy. It does exist as a fixed point, just like with this specific geometry to the function, but if you move it even a little bit, there's no fixed point there at all. All right. The index in this way is some kind of, you could think of it as like an algebraic measure of the multiplicity of a fixed point or something like that. There's some analogy with like repeated roots of a polynomial. You can have sort of a positive fixed point or a negative fixed point. It is related but not the same as the idea of attracting and repelling fixed points. their relationships, but it's not like a +1 is always attracting or something like that. All right, great. So when we change the f by a homotopy, actually the fixed points, they can dance around quite a bit, and sometimes they can go away, they can combine with one another, they can disappear. You can create them out of nowhere if you create new intersections with the diagonal, but the total index sum will always stay the same, because no matter how you change the fixed points around, when they collide, they add up, right? So whatever the total sum is that you started with, no matter how you move the function around, the total sum will always stay the same throughout the motion. All right? Actually, that number, that total sum, has a name. It's called the Lefschetz number, which you might have heard of from if you've done some algebraic topology before. I'm not really going to talk about the Lefschetz number, but the total index sum will stay the same. All right? Hope I'm doing all right so far. Okay, so that was the first ingredient. I said there were two ingredients, the fixed point index, and then the next ingredient is called the Reidemeister Classes, which is, where this Reidemeister is, you know, a person's name, the same Reidemeister from knot theory. So the Reidemeister Classes, unfortunately, is only interested when X, the domain, is not simply connected. That means that this only is interesting when the domain is a space which kind of has holes in it. And so, but I still want to stay in one dimension. So, sorry, my beautiful face is in front of the words here. I think this might be the only time that's going to happen. Instead of the pictures in R, that's what it says behind the curtain here. Instead of pictures in R, we're going to use S1, the circle. The circle is a one-dimensional object. I mean, locally, at least nearby at points, it looks like a line, but it sort of wraps around onto itself. All right. And to draw these pictures, rather than drawing circles every time, I'm going to represent the circle as just the interval, the closed interval from 0 to 1, with the endpoints glued together. So this is a traditional topologist's way of thinking about the circle. So I'm going to think of it as more like an interval, but every time if you're traveling along here and you go off that side, you come back on the other side. All right, so this is how I'm going to view this circle. So what that means is I can still graph our functions that I want to talk about, only this domain now is not the entire line, it's just an interval, and when I draw the function, it has to kind of wind around properly, which is to say, if I wanted a function that looks like this, maybe, when I get to the right-hand side, it has to end up at the same point here, because these 2 points on the picture, they look different, but they're actually the same point, right? Because I'm gluing together the 2 ends of the domain. All right, so that would be a legal function on the circle, whereas, you know, this is not a continuous function on the circle, because this endpoint doesn't match up with that endpoint. And also, the codomain is also going to be the circle, because of fixed point theory, you always have to have a function from one set onto itself. So that means that I'm also going to consider, vertically speaking, the top line here is glued together with the bottom line. So a typical function I'm going to talk about would look maybe something like this. It can do that kind of stuff. All right? This doesn't look continuous, but it is, because when I go up here, this point is actually the same as that point, and it continues like that. All right, so these are like ordinary functions, but they're kind of like wrapped around a circle or something like that. I say they're like wound up. All right, so that's what we're going to be talking about really for the rest of the time here. Now, the second ingredient, the Writemeister Classes, it tracks how many windings we do before you arrive at the fixed point. And I'm going to write it in this way. I'm going to use this rho. So I'm going to write rho for 1 winding, rho squared for 2 windings. I'm writing this as if it was like a group element, because it really does, it is representative of a group element behind the scenes. All right. So, for example, here's a typical function on a circle, and these points here, these fixed points, this is another thing that you assign to each fixed point. The Reidemeister class is how many times did you wind around before you met that fixed point. So in this case, the function you think of as like starting here. And in order to get that point, you got to go around the circle once. That's why this one has Reidemeister class given by rho. one winding, all right? This one also is one winding because I didn't, go around again before I got to that point. Same for this point. This is also one winding. But this one is now two windings before you got to that point because you had to go around again to get there, all right? So these are the Writemeister classes. It's called classes because, as you'll see in a moment, there is some kind of equivalence relation that we need to do to make this work really. But I will point out, these things are also preserved by homotopies. That is, if I change the function a little bit, I'm going to see if I can grab them here. Notice when I wiggle this around, as before, the fixed points, they do wiggle around a little bit, but those classes don't change. Like, it took one winding to get to this point, and if I wiggle that point a little bit, it still takes one winding to get to that point. All right, so these things also are kind of an appropriate thing to consider in a topological fixed point theory because they are preserved by the homotopies. And here's where we get to the equivalence relation. Actually, what I said right there is not 100% true. They are preserved, except there's one case in which this thing, the Reidemeister class, can change. Here I drew the same picture, but I sort of copied it across. That's because I'm about to do some fancy jiggles where I wiggle the function sort of all the way across. Remember, this function, I'm only drawing a piece of it, but it sort of is replicated as you go off the as you go off the right end of the picture. You're supposed to come back on the left end. But anyway, can I say, I'm going to try and show how, come on now, how these Writemeister classes, they actually can change. All right. For instance, this one, I want to focus on this one right here. That point right there has to wrap around twice before you get to it. Watch what happens to that point when I move the whole picture to the right. Dropped it. Am I doing it? No. One more try. Sorry, I've never tried to do this kind of wiggling and jiggling during a talk. All right, see that point? You should be looking in the upper right of the box. You see that fixed point is approaching the upper right corner, and it leaves the picture. Now, that fixed point didn't actually disappear. In fact, that fixed point, which used to be up here, when it left the picture, it became this point over here. All right, and that's just because of the way this function wraps around. That looks like it's jumping. It's actually not jumping. That's the same point. So this fixed point over here, which before I said had to wrap around twice before you get to it, turned into this fixed point over here when I jiggled it. And now I would assign this as either one wrap or two wraps, depending on how exactly you count this. So this is the case in which this row can actually change when you move the picture. If the fixed point sort of leaves one side of the picture and comes back, if the fixed point itself wraps around the picture, then that class will change. Now, fortunately for us, this type of change is very predictable. So it is a fact that some of these winding numbers are equivalent to other ones. And in that example that I just did, you can work this out. Rho to the n is equivalent to rho to the m. So I'm using these brackets as like equivalence classes. They're equivalent when those two numbers are equal mod 2. And in more generality, so these are called the Reidemeister classes. They're called classes because there's an equivalence class for them. More generally, I'm talking about just the circle. Now on the circle, there's really only one way that you can wrap around it. There's just a circle. You can wind around it. I suppose you could go the opposite direction, but more generally speaking, a more complicated domain will have many different holes in it, and there are different holes you could wrap around, and you could wrap around things in much more complicated ways. And so, more generally, these rows, they will be elements of a group, the fundamental group, which is the group of all loops in a space that can go around all the different holes in all the different ways. All right, and I said the classes, judging when classes are equivalent is very predictable, and if you work out all the details, it's this equivalence relation. Two classes are equivalent if and only if there exists some other class gamma such that alpha equals f sharp of gamma times beta times gamma inverse, where this f sharp is the induced homomorphism on the fundamental group. It's fine if you don't know what that means. Just in case you want to know. This is referred to as they are equivalent modulo twisted conjugacy. This right here, actually, if you look closely, it looks like a conjugacy relation. I have gamma, beta, gamma inverse. It's not quite conjugacy because of this function right here. So this is called twisted conjugacy. If the F is the identity homomorphism, then it is real conjugacy. But for other functions, it's something slightly different. And there are actually people who just focus on the algebra of this, all of this stuff. Like their whole thing is figuring out for various different groups and homomorphisms how do you compute the twisted conjugacy. And I've written a few papers like that, which have no topology at all. It's just about this this algebra. And this is kind of a nice thing about this discipline in general. You have the fixed point index, which is very much a geometrical thing. It's about two things crossing over each other. And then you also have the Writemeister Classes, which is a more or less purely like group theoretic algebraic thing. And so you can, you know, if you get tired of the geometry, you can do the algebra for a little while. I like that. Okay. Anyway, when fixed points combine, what happens to the Reidemeister class? Remember, the fixed point indices were numbers and they add together. What about these classes when they combine? Well, this is a bit of a simpler situation, but say I have these two points right there, which each of them, their class is rho, and I can combine them by kind of moving the picture to the right here. You'll see those two fixed points are getting closer and closer, and eventually they will combine right here. What happens to the fixed point class, the Reidemeister class of this combined point? It's still rho, like it's still wrapped around one time there. So the moral of the story here is really nothing much happens to them. They don't like add together. They're group elements, so you can't really add them together. But you can say they have to be the same in order for them to combine. Like if the 2 points are going to combine, they have to be like right next to each other on that picture. So the Writemeister classes need to be the same in order for the 2 points to combine. All right? I mean, of course, the same according to the equivalence relation. So anyway, those are the two main ingredients, the fixed point index and the Writemeister classes. And we can do these things sort of together. So if I were to consider these together, this point right there would be, I hope you remember your fixed point index, this would be a -1 and a rho, right? -1 because the graph is going up through the diagonal. That counts as a -1. This is a +1 and a rho. This is a -1 and a rho. And this here is a -1 and a rho squared, right? So we want to consider both of these things at the same time. In fact, it is these combine very well when we formally multiply them. So rather than what I just wrote before, it had sort of like a comma between them, I'm actually just going to write negative rho here. Here I'm going to write a positive rho. Here I'm going to write a negative rho. And here I'm going to write a negative rho squared. What does negative rho mean? Well, it just means it's a rho with a minus sign. But for reasons which we're about to see, it works really well to just kind of combine them in this way, even though this just doesn't really mean anything by itself. It just means I combine them. All right, but something you'll notice, the total sum here is preserved under the homotopy. That's because, like, if I were, you have to imagine, if I were to combine these 2 points, what would happen? They would add together. You'd get minus a rho, a plus rho, and they would cancel out, which is exactly what we would want because you can combine these 2 fixed points and remove them. So the total sum here, when you add everything up here, what I mean is just you just do minus rho, plus rho, minus rho squared. And you add this up. Actually, we get some cancellation here. We end up with minus rho squared. And that sum right there, even though it's not a number anymore, it's just like a weird thing with coefficients, that sum right there is preserved under any homotopy. And so yeah, what is it? It's not a number. It lives in this abelian group ZR of F, where R of F is the set of all Reidemeister classes, that is rho things, and this Z indicates they can have integer coefficients in front of them. And this is a group meaning you can add them up like I just did. All right. And this actually, what I just said, the sum of the things, that is the Reidemeister Trace. That's what this talk is allegedly about. This is called the Reidemeister Trace, and we write it this way, RT of F. So in that example that I just had, the Reidemeister Trace is that. It's negative rho. I put the brackets, that means the equivalence class of rho, and then minus rho squared. And the fact is that you can change that function any way you like. You're not allowed to break it, but you can wiggle it around however you like. And the sum of all of those little things will always add up to this. That's the point of the Reidemeister trace. All right. Here's a fancier one. I just want to do another example. So if I did this one, this is a minus row. And if we were all in the classroom together, I would ask, what do you say? What is this or that? This is a plus row. This is a minus row. This is, I guess, a minus row squared because I had to go across the top to get there. This one right here has a 0 index. Its winding number would be 3 times around. So this is actually 0 row cubed, which of course is just 0. And then this one, it wound back around down there. This is going to be now a plus row squared. And so what's the Reidemeister trace here? It's you just add all of that up. Minus row, minus row squared, plus 0 row cubed, plus row squared. And a lot of this will cancel. Actually, almost everything will cancel. Those cancel, this, and this is 0, so this is just minus row. So apparently this function, its Reidemeister trace is just minus row. I suppose technically I should say the equivalence class of row. All right. That's how we do it. Now, this is not the one I just did. The one I did 2 times ago. I rearranged my slides, I think, in a bad way. The one I did 2 times ago, the Reidemeister trace ended up looking like that. I will just say this is similar to the Lefschetz number. This is something I mentioned before. When you just add up the +1, -1s, the index, but you don't consider the wrapping around, when you just add up the numbers, you get the Lefschetz number. You can still see the Lefschetz number in here because you could just disregard these windings and only consider the coefficients. And in that case, you can say, in this example, the Lefschetz number is 2. So the Lefschetz number is always equal to the sum of the coefficients in the Reidemeister trace. So the Reidemeister trace is like a strictly, it's a generalization of the Lefschetz number. In fact, it has, at certain times throughout the 20th century, people refer to this as the generalized Lefschetz number, and then somehow they changed the name of it. I don't know. But the Reidemeister trace is actually better. It's a generalization. It's better because it is possible that maybe the Lefschetz number is 0. That is all the +1s, -1s, they all cancel out. While it turns out when you see the Reidemeister trace, you realize that maybe there was a negative Reidemeister class together with a positive Reidemeister class. And why this gives more information, because if the Lefschetz number is 0, that suggests that maybe there are no fixed points, or there are fixed points and they just somehow cancel out by coincidence. When you see the Reidemeister trace is this, you know for sure there has to be at least 2 different fixed points. One with the Reidemeister class of alpha and one with beta, and those two can never be combined. All right, so the Reidemeister trace can give you more information than the Lefschetz number can give you, which is why it's better. All right. Yeah, like in that case I just said, from the Reidemeister trace we could realize there will be at least 2 fixed points, whereas the Lefschetz number we wouldn't be able to conclude anything. So in this way, the number of terms in the Reidemeister trace tells you how small the fixed point set could possibly be. Like in this case, there are 2 terms, which means there must always be at least 2 fixed points of the function. All right. That number actually is called the Nielsen number, which has been sort of the major focus of topological fixed point theory for most of its lifespan, the 20th century. And it's this whole field is sometimes called the Nielsen theory. In manifolds, yeah, this is just a little Nielsen theory fact. If your domain is a manifold that does not have dimension 2, then this number, the Nielsen number, can be achieved by homotopy. What that means is when you see 2 terms, only 2 terms in the Reidemeister trace, that means actually it really is possible to change your function to have exactly 2 fixed points. That's what I mean by the number can be achieved by homotopy. There are weird examples that show that's not always possible in dimension 2. But in all other dimensions, 1 and also everything higher than 2, it is possible. All right. So in my remaining 10 minutes or so, I want to talk about why is the Reidemeister trace called a trace. Actually, it is a trace of a matrix. And I want to show you how that works in our remaining 10 minutes. It is the trace of a matrix. The trace, remember, is just you add up the diagonal entries in a matrix. When I first heard about the trace, I thought it was kind of stupid. Like, how could that possibly be useful for anything, because it's such a simple thing to do to a matrix. I had just learned about the determinant, which is complicated enough that I thought like, oh yeah, I'm really doing something when I do the determinant. That must mean something. But then I learned about the trace, and I was like, that's stupid. But the trace actually, it is important in a lot of settings, and it turns out that thing, the minus rho plus rho squared, whatever, you can get that by taking the trace of a matrix. So what that means is the Reidemeister trace is actually very easy to calculate, even in high dimensions, without looking at the picture. If you can describe your function in the right way, you have to be able to translate your function into a matrix. So in order to do this, you first have to triangulate your space X. What that means is you just kind of divide it into little chunks, which are either triangles or some other nice regular shape. And you make it so that F maps each of those little chunks, which is called a simplex, into another simplex, or maybe a union of simplices. So on a line, it's easy. You know, triangulation, they don't look like triangles. It just means you divide your line up into little subintervals, and you make the function so that it takes each subinterval onto another subinterval in the codomain, or maybe a union. So, for example, here's an example of a nice function of a, you know, after I subdivide. So I subdivided the domain and the codomain into 3 bits, and this function now has the property that, like, for instance, this little bit here goes onto the union of these 2 bits. And this bit in the middle actually goes onto the union of all 3 of the bits, and then this little bit over here goes onto this little bit over here. Such a map is called like a cellular map after subdividing or something. All right. Basically, any function you can think of, you could wiggle it around so that it looks like one of these, right? You just basically straighten out all of the lines, and then it will look something like this. So this is not a big deal to rewrite your function in these terms. And what we're going to do is write down in terms of these things. So I labeled these vertices and edges. I have 3 vertices, V1, V2, V3, and 3 edges. There's also one on the end, but that's actually V1 again. So I didn't label the point on the end. And I'm going to write these 2 functions, F0 and F1. F0 refers to how my function behaves on the vertices. Vertices are 0-dimensional, that's why this says F0. This is how it behaves on the dimension 1 things. So what is F0 of V1? That means where does V1 go when I do the function to it? It goes to V2. So this, I'm going to fill in the blanks here. This is V2. F of V2, you can see on the graph here, V2 actually goes to this point here, which is V1. So this is V1. F of V3, V3 also goes to V1. So this is V1. F of E1, that means this edge here, and it goes to this thing, which is the union of E2 and E3. And because I want to write this like a matrix, I'm not going to use a union. I'm going to write this as if I'm adding things up. So this goes to E2 plus E3. And now I realize I forgot to do a little something. Sorry, this first one was right. Go back to the vertices. I want to account for the winding around too. So this V2 goes to V1 after 1 wraparound. So I'm going to write this as a row V1. Sorry about that. And then I told myself, I was going through this last night, and I said, don't forget to put the thing in there. And I did forget to put the thing in there. And then here, this V3 goes to V1, but after 2 wraps. So this is row squared V1. All right, I am keeping track of the wraparounds. Okay, and then E1, that's okay, because these ones actually did not wrap around. This one, E2, this one does, it hits everything after 1 wraparound. So it's going to be row E1 plus row E2 plus row E3. And then the last one here is E3 goes just to E1, but after 2 windings. So this is a row squared E1. All right, I hope I got those right. Not hard to create this, you know, and if you're using a computer or something, if you had some kind of encoded version of this function, it's very easy to compute all of this information here. Just where does each piece go? All right, that's what I just wrote. I hope I got it right. And I will invite you to consider, you can turn this into 2 matrices. So over here, I'm going to consider these V1, V2, V3 to be like a basis. And over here, I'm going to consider E1, E2, E3 to be like a basis. And we can make matrices. So the first one would look like, in my first column, I'm going to write what happens to V1, and it does this. V1 becomes just V2. I think of this as 0 V1s, 1 V2, 0 V3s. All right. What happens to V2? It goes to row V1s, 0 V2s, and 0 V3s. And what happens to V3? It goes to row squared here, and 0 and 0. So that's the matrix of F in dimension 0. And then the matrix of F in dimension 1, I do the same business. The first column is these guys. E2 plus E3 gives me a 0, 1, 1. Next column is rows everywhere. And the last column is row squared, 0, 0. All right? I made matrices out of my function. And then, actually, I want to bring to your attention, you can see the fixed points and where they appear in the matrix. In this example, I have only one fixed point. Ask yourself, where did that fixed point come from in terms of the bits of this function? It came from the fact that E2 down here mapped onto E2 up here, right? A fixed point will arise whenever one of your little bits is mapping onto itself. And I can identify in the matrix where that happened is right here, right? It is that this fixed point corresponds exactly to that term in the matrix. And maybe now you can see why the trace is going to be important. The trace, remember, is the sum of all the diagonal entries. You just add up these guys and these guys. The diagonals are important because these fixed points arise when one of the bits goes onto itself, and such a thing always arises as something on the diagonal in these matrices. The fact that I have all zeros elsewhere means that none of these other bits ever mapped onto themselves, and so they generated no fixed points. All right? So this is what I just said. Any non-zero diagonal entry will generate a fixed point. So we expect the traces of those two matrices to be meaningful. And it turns out this is a theorem proved by Vecken in the 1920s. Actually, if you add up the traces in this way, you take the sum of all those matrices, their traces, and you alternate the signs. It turns out that actually adds up to the Reidemeister Trace, what I was talking about before. And this is why it's called a trace. It's not really a trace of a single matrix. It's a sum of a bunch of different traces with alternating signs. All right. So I got 5 minutes just to finish off. Let's just try a fancier example here. So in this example, if I look at the picture just by identifying the fixed points, this is a minus row. That's one time around. This is a plus row. This here, oh, that's not a fixed point. This is my other fixed point. This one is plus, but it's still just row. I only have wrapped around once by the time I get there. All right. So just looking at the picture here, we can see the Writemeister trace is minus row, which is row. All right. Those are that's the Writemeister trace. If you look at the picture, all right. Really, when you're doing this sort of in real life, you don't have the picture to look at because you're talking about some high-dimensional thing. So the trace formula is actually easier to use than looking at the picture in most cases. Let's try to do the same thing using the trace formula, and hopefully we'll get the same answer. In this case, I'm going to write out my matrices. So F0, this time I have 4 little bits in the domain, so this is going to be a 4 by 4 matrix. And in dimension 0, you're looking at the vertices. The first vertex goes up to the last one. So this matrix will look like that. The next vertex here goes up to the third vertex, but after one wraparound, so this looks like this. The next one here goes to the first one after one wraparound, so that looks like that. This one, the last vertex, actually goes onto itself, but after one wraparound, so this looks like this, right? I think I did that right. And then the edges. I look at the first edge here goes to this guy plus these two. So these two are after one wraparound. This is not after one wraparound. So that top little bit there is the last numbered edge. And then I have the first two after one wrap. So it's row there, and a 0 there because it never hit this edge. All right. The next one, this edge here hits the last 2 edges, but it's going down. This is something I didn't mention before, but when you make these matrices here, you have to account for the orientation of the direction of the edges, right? Here, this edge is actually mapping onto these ones backwards. So this becomes a zero, not a zero. It's 0 for these two. It does hit those other two with rows, and I'm going to put negative signs because the orientation is backwards when it hits those. All right, the next one, this one hits all three of the first edges with one wrap. So this is row, 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 0. And then finally, the end, it hits this one with a row, and then all the other ones with a row squared. So like this, row squared, row squared, row squared. Sorry, I did that backwards. I didn't like the looks of that. It's because the row squareds are these ones, right? The one that it hits before the wrap is the last edge. All right, got to get it right. Okay. All right, those are the matrices. So it works. Oh, I didn't finish. I'm going to add together the traces in that way, and you have to alternate the signs. So what I'm going to do is the trace of the 0 dimension, and then minus the trace of the 1 dimension, because you add up all the traces, but you alternate the signs. And what do you get here? So the trace here is just row minus the trace here is a lot of stuff. Row minus row plus row plus row, right? And a bunch of stuff will cancel, right? This row minus row, I end up with row minus row plus row, which is negative row. Is that the same answer I got before? I think it is, right? What? Oh, I got the sign wrong here. Thank you, nobody, for correcting me before. That should have been a negative. This should have been a negative. I'm so embarrassed. This is negative. Now it makes sense. That was supposed to be the easier one. I messed that up. I went through the whole calculation. I got the same answer. That I was trying to demonstrate Vecken's theorem. When you add up the traces, you actually get the same answer. All right. So it works. I just thought I'd tell you in the last minute or so. The paper I was working on for most of the summer is about the Reidemeister trace of an n-valued map. An n-valued map is a function where you get n different answers every time. So if you do like a little vertical line test here, I tried to draw this. I hope that this actually worked. This is a 3-valued function because every point in the domain goes to 3 points in the codomain. All right. And you can probably imagine you can do more or less the same thing with a function like this. Really, what is much more complicated is the Writemeister classes, because it becomes a lot more complicated to discuss how many times did the thing wrap around. Actually, on a circle it's not so bad, but on more complicated spaces it's a lot more complicated. So that's really where the complications arise when you try to generalize this to multi-valued functions. All right, I think that's all I got. So thanks for your attention. Anybody have any questions?
Yes.
Yeah, I see Paul.
Could you go back to the previous slide?
Here?
Yep.
Yeah.
So the n-valued functions, are you requiring them to be continuous in some way?
Yeah, so this is continuous in the sense that these lines actually do sort of connect up with one another. I mean, I drew this by hand, so it's not perfect, but every time you go off one side, you actually do come back. I think I just did one full trip around. You can, so the typical way that the continuity is described in this situation is you view your function as a map of x into x to the n, three Cartesian 3 copies of x. So it's a triple of points, and you just force it. You say I only consider functions where every domain value goes to 3 distinct points. And then you can just say it's continuous on that with respect to the Cartesian product. But what it amounts to in one dimension is still the sort of all the lines meet up.
And so another sort of consequence of that is that these lines can't cross, right? So
Yes.
Because if they cross, suddenly you go down from 3 distinct values to two
Right.
distinct values.
Yeah, and that's it's a real issue. If the lines crossed, then suddenly you would have to come up with new ways of defining the fixed point index at the crossing points. Oh, it just went out. Sorry. Yeah, that. I mean, you could still try to think about that, but it becomes a whole different ballgame.
So doesn't the two of those two aspects combined, that you have to be continuous and then you can't cross, doesn't that sort of chop up your picture into sort of ribbons?
Yes. Yeah. So in the
insert-
one-dimensional case, any such, and this was worked out actually by my dissertation advisor, although it's not that hard. This was like an undergrad research project, I think. It is a fact that any such function can be written like this, basically. All the one that I drew looks kind of interesting, but by a homotopy you can straighten all the lines out so that it has a lot of regularity to it. So in one dimension, actually, the entire any question you want to ask is already answered. In higher dimensions, it's much less clear. Any other questions?
Yes, can I ask, like you mentioned a little bit about there's something special with dimension 2?
Yeah, there is.
Can you say something a little bit more about that?
Yes, this happens in a lot of different areas of topology where the dimension 2 is harder than other dimensions. I think like the cute slogan is in dimension 1 is not big enough to get into any trouble, and in higher dimensions you have enough room to get out of trouble, but in dimension 2 you're kind of stuck. And if you think of things in terms of moving stuff away from the diagonal, here my domain is dimension 1, but this whole sort of space that I have to work with in moving things around is dimension 2, right? In 2 dimensions, so if in dimension 3, when you're looking at those intersections, say the graph intersecting the diagonal, this intersection occurs inside of basically R6, or a 6-dimensional manifold. And in that case, you have a lot of opportunity to move the function away from the diagonal in certain ways. So it's not actually always possible to remove every fixed point, but at least it's a lot easier to straighten things out. In dimension, and it gets even better. In dimension 4, you're in an 8-dimensional ambient space. But it turns out in dimension 2, you're only in sort of 4 ambient dimensions, and it's not always possible to do the same movements that you want to do. This is my vague explanation. There's something there's something called the Whitney trick, which is a trick used for moving things around, moving manifolds and changing intersections of manifolds. And the Whitney trick is really why the Whitney trick only works in dimensions above 2. And the proof that Becken did about the minimization fundamentally uses the Whitney trick. And there are counterexamples in dimension 2. All right. Thank you all for coming.